In this video, I talk about how I parallelized the simulation code in my game, Steam Revolution. I measured accumulated times after running 1 million simulation ticks. This makes the math nice, so that the number of seconds taken equals the number of microseconds per simulation tick. In the world map with 214 trains, parallelizing my code made the time go from 43.2 seconds to 17.7 seconds on my computer, a 2.4x speedup. Speeding up the simulation via multithreading is challenging for a few reasons. First, the duration of each simulation step is very short, so the overhead of parallelization is difficult to overcome. Each simulation step is also composed of multiple interdependent stages that further reduce the time per parallel section. There are 6 parallel steps per tick, so in 43 microseconds, that's an average of about 7 microseconds per step. Second, the simulation is not trivially parallelizable, because trains interact with each other and with shared resources such as sections of track and industries. Third, results of the simulation must be deterministic and identical between serial and parallel versions. Rerunning a simulation should give the same score every time to make playing the game fun. Also, server verification of results requires the server and client results to match. I'll give an in-depth description of the challenges to making each part of the simulation parallel and the strategies I use to overcome them. Although I'm specifically describing my solutions to my problems, they may provide inspiration for parallelizing your own code. This video can be watched on its own, but it builds on my 3 previous videos. You may want to watch those for more context. In devlog number 6, I described the optimizations I performed to get my single-threaded optimizations to run 17 times faster. This parallelization is a continuation of that optimization effort. In devlog number 7, I describe how signals work in the game. Here, I describe how the tracks are split into segments and blocks, the mechanics of signals, and an overview of the simulation steps relevant to signals. In devlog number 8, I describe how I implemented a low-latency parallel for library for my game that outperforms OpenMP and PPL. So, if you want to pause and watch those first, I'll wait for you here. Okay, welcome back. But before getting into nitty-gritty implementation details, it's probably a good idea to give an overview of what the game even is. You know, just in case you didn't actually watch those videos I mentioned. Steam Revolution is a game about building train routes to transport materials and goods between industries and cities. The goal is to deliver a set number of goods in a level as quickly and efficiently as possible. This consists of an iterative design process of building routes, simulating, tweaking, simulating, etc., until you are satisfied with your results. When iterating, you often want to run the simulation as fast as possible to simply check your score and check your results against the online leaderboard. This is why making the simulation code run as fast as possible is so important for my game. Okay, so before I talk about what the parallelization speedups I achieve are, it's important to discuss what I'm achieving them on. The computer I'm doing my testing on is a Ryzen 2600X. The picture I'm showing here is, well, it's of a 2700X, but that's exactly a 2600X with 2 of the cores disabled. They're actually the same die. This die consists of 2 clusters of cores. In my case, it's 2 3-core clusters. So when I talk about the speed of a cluster, that's where I'm running with 3 threads, 1 thread per die in 1 cluster. When I talk about running on all of the big cores, that's a total of 6 threads then, 1 per core. And finally, when I say all, that means all of the logical processors, because each one of the cores presents itself as 2 logical processors via hyperthreading. The important thing to know here is that the communication latency between cores within a given cluster is much lower than when you're talking between different clusters. So you would expect that the overhead from parallelizing when you're running on a single cluster is going to be lower. With that background out of the way, we can talk about the scaling that I achieved. I generated timings from 4 different sets of data. The first is a small level with only 3 trains, and this was very fast in general to run. In fact, for the single-threaded run, it took about half a microsecond per tick. The test with 26 trains was one of the city levels where I had filled out the level to be about as optimal as I could. So this is the typical case of a completed level. The test with the 151 trains was the world level where I had filled it out as much as I could before I had started all of my optimizations. And I had stopped because at that point it was just going too slowly for me. Unfortunately, that save game no longer exists. It was overwritten. But I then continued to complete the entire world map, and that resulted in 214 trains. So this isn't the most trains that you would ever have. It's not an optimal solution, but it is a complete solution of the world map. You can see that when I got to 214 trains, that the time per simulation tick had climbed to 43 microseconds per tick. When I was then running on a cluster of cores, then this reduced to about 17.5 microseconds. When I then increased the number of threads to run on both of the clusters, so that's the big times, and all of the logical threads in the computer, you can see that the times actually stayed about the same or slightly increased. That means that when communicating out of the local cluster, that the overhead of communication outweighed the benefit of having more threads doing work. I can also reorganize the graph in a slightly different way. Here I show the speedup of the multi-threaded solutions relative to the serial solution. What that means is that if the value is 1, then it's running the same speed as if it was in a serial code. And if it's higher than 1, then it's going faster. In the case of 3 trains, you can see that in all of the multi-threaded solutions, it's actually running significantly slower, about a half to a third of the speed. However, in the largest number of trains, we can see that in the cluster it gets to about 2.4 times faster. And recall that a cluster for me consists of 3 cores. That means that I'm getting actually pretty close to the ideal speedup factor. However, that speedup stays about the same or even drops as I continue to add threads. So what that tells me is that for my problem, that I should stick to a single cluster because adding more just makes it go slower, in fact. This is true even for the entire world map with a lot of trains, and I think that even if I have more trains, eventually if I used every single core that it would win out, but that's not going to be a very typical case, and I don't think it would win by very much. Those were the overall times for a simulation tick, but recall that a simulation tick actually is composed of several different parts. So let's go into a little bit of detail about what those parts actually are. There are 10 steps in total, some of which I was able to parallelize and some of which I couldn't. The first step is to update the track occupancy with what trains are in what parts of the track. Next, I propose a new location for all of the trains. Then, trains that are waiting at a signal resolve their loading and whether they can enter through the signal. Based on those results, then trains will commit their movement steps, and that means that if a train's movement was valid, that the proposed location is then turned into the actual location. Collision detection is then done between the trains to check if anything hit anything else. And then I add any new trains and cars to trains as they're coming out of the depots. Now that all of the train work is done, then everything else needs to be done. And that means updating the industries of consuming and producing resources. Cargo loaders need to take cargo from the trains to the industries or vice versa. We need to update the state of smoke that's been emitted from trains. And finally, we need to check and update the game state to see whether a level has been completed. Here I've color-coded the steps based on whether I could parallelize it or not. And the steps marked in green are parallelized, the ones in red are not. The first 5 steps are the ones that actually take the most time and are the ones that involve the updating of the trains themselves. I didn't parallelize adding cars and trains, but then updating the industries I parallelized, and then the remaining steps of updating cargo loaders, removing smoke, and updating the game state were also not parallelized. Without context of how long the steps actually take, it's hard to say whether that's good or bad. So here's a graph of the times when running the code serially versus parallel with the largest 214 train test case. What you can clearly see is that the parallel times shown in red are typically much lower than the serial times shown in blue. As you may recall from the previous slide, the first 5 of these times are the ones that I was able to parallelize. I wasn't able to parallelize adding trains and cars, and then updating industries I was able to parallelize, and then the final 3 steps I didn't parallelize. What you'll notice is that the things that I didn't parallelize are also all things that ran extremely quickly. So the amount of overhead from running them serially is not very high, and in fact that's part of the reason why I didn't parallelize them. The thing that you can also notice is that the thing that took the most amount of time, I was also able to achieve a pretty good speedup of. This is, I think, somewhat to be expected because the overhead in communication is going to be lower in that case, but it's also quite good for the actual final results. What I think is also somewhat impressive is even for extremely short duration things, I was able to achieve a speedup. In particular, updating the track occupancy was not something that was entirely trivial to parallelize, and it took only 3/4 of a microsecond in the serial code, but I was able to reduce that to half a microsecond in the parallel code. Before I go into details of how I parallelize every step of the simulation, I want to talk about some generic sources of overhead. The main source of overhead is going to be from memory transactions that involve either sending the data in cache lines or the status of cache lines. Specifically, just the starting and stopping of a parallel for loop has a large amount of overhead associated with it. I made a rather in-depth video about that in devlog number 8, so if you'd like to learn more about it, please go check that out. But the idea is that in addition to just starting and stopping jobs, any data that's read or written by a thread is also going to result in communicating that data across the bus. This means that if you read or write any data about the train state or any other simulation state in one thread and then read it from another, then that's going to involve some communication overhead. This also means that if you dynamically distribute the work between threads instead of statically partitioning it, then in addition to the overhead from just saying, hey, this job needs to run on that thread, you also get the overhead of different threads reading random different data. And if you had statically partitioned the threads over, say, the trains, and if you run two different parallel for loops over the set of trains, if you statically partitioned it, chances are that the same thread would get assigned the same train, and you wouldn't have any data transfer because of that. But if you dynamically partition your data, then you have no guarantee that the same thread is going to get the same train, and so you actually get a double hit of data transfer. So, although the idea of dynamically distributing work sounds very appealing in that if you have non-uniform size of work items, that, yeah, it sounds good that if a thread finishes early, then go ahead and pull the next work from the queue. In reality, for extremely short duration workloads like I have, the overhead actually just kills you, and in none of the cases that I have in my simulation was I able to do anything even approaching the same speed. Dynamic was always clearly worse. Another source of overhead is whenever you get an exclusive lock over a piece of data. The primary reason why this is slow is because acquiring a lock requires communication between threads. So even if you do an extremely short duration lock, you still have to perform an atomic read, modify, write operation, and that's going to be the source of overhead. If you want to have more details on how I actually implement a lock, please see my previous video. The other source of overhead is the time actually spent inside of the lock, right? This is an effective serialization of what would otherwise be parallel code if any other thread is waiting on the lock while it's owned by another thread. Thus, you want to minimize the amount of time that you spend in a lock. For me, what this typically means is that if I'm, say, adding to an array that's protected by a lock, I set up everything that I can first, and then I acquire the lock just in order to add the data to the array, and then I release the lock. Perhaps less obviously, there are some more sources of overhead. And one of those is that it's necessary to modify your algorithms to support parallel execution. In my case, that involves doing some sorting by IDs of trains and splitting work into independent tasks. These are things that would not need to be done if it was running serially. Fortunately, in my case, they don't provide a lot of overhead, but depending on your actual algorithm, they may be better or worse. So this does affect my serial timings in my benchmarks slightly because those are running the parallel code but serially. It doesn't matter too much, but you should be aware that it does have some small effect. There are also some external factors that don't necessarily directly have to do with your program. One of those is that simply running on multiple different threads means that the CPU is going to be drawing more power and producing more heat, and that may result in the CPU or the operating system downclocking the CPU to either conserve power, to stay within a power budget, or to avoid overheating. This is something that will even affect the serial portions of your program, either if you have the different threads running in a busy wait, or even if you have all of the threads asleep, the CPU might get heat soaked and then run at a lower clock speed because of that, because of a hysteresis that previously it had been consuming a lot of power. And finally, you need to recognize that your program isn't the only program running on a computer, and so there's going to be contention potentially with other programs. Some of those might be the operating system itself or critical services, and some of them might be, a web browser or another game running or who even knows what. Alright, so that covered the sources of overhead, but I would also like to talk about how I handle errors during the simulation, because that's something that is going to generically apply to multiple different parts of the simulation. The way that I deal with this is fairly simple. Whenever part of the simulation runs into an error, it will then add an error marker to an array. The error marker is fairly simple. It's a struct that has the location that the error occurred in the map. It has a string that stores what the title of the error is, and a string that contains the text that should appear in the text box. If there are any errors in the array, then when a simulation step is started, it will simply return and do nothing, and the effect of this is that the simulation stops. Of course, this is a shared global array of errors, and so I put a mutex around any access to that array. In all of the details of the simulation steps, I'll try to also note whenever a step can create an error. I won't go into a lot of detail about how that works, but just know that I covered it here. Next, I'm going to go into the details of how I parallelized all of the different simulation steps. But if you've liked what you've seen so far, go ahead and hit the like button. The first simulation step is to update the track occupancy. This actually consists of updating two different things, both the segments and the blocks of the track. The segments are the sections of track that are split by signals, and blocks are a collection of segments that don't have any signal separating them. Each segment and block contains a spin lock that a thread must acquire before modifying its occupancy list. Modifications to the list are relatively uncommon, and so there's not a high overhead from acquiring the lock. I iteratively update the occupancy lists, which means that I only modify a list when a train enters or exits a segment or a block. In order to know whether I entered or exited, I also need to keep a copy of the previous position so that I can compare a difference. So, in a parallel for over all of the trains, at the front of the train, when that enters a segment or a block, I acquire a spin lock and add to the segment or the block. And at the back of the train, when I exit a segment or a block, I also acquire a spin lock so that I can remove the entry for that train. So this is one of the basic mechanisms through which trains will communicate between each other about where they are. The next step of the simulation is to propose a new location for a train. This step actually has a couple of different subcomponents to it. The most important thing to understand is that the train state is split into both a proposed location and a current location. This is important because while proposing a location, trains can read the current location of other trains and will just write to its own proposed location. Because the data they're read from and written to are different between the different threads, there's no source of contention or non-determinism. This is important because the trains actually do read each other's locations, and in particular, this is to calculate the follow distance. When there's a free signal, it's possible for two or more trains to be in the same block. And on the same track, if one train were to run into another, it will not run into the other train, it'll simply follow it. In order for that to work, the trains need to know where each other are. And they determine this through the occupancy that was written to in the previous step. The search for the next train that a train might run into is somewhat slow to actually figure out, and so the trains don't do it every tick. Instead, they know what the distance is to the next train and their maximum speed of travel, and that provides a lower bound on how many ticks until the train might have a collision. So that value is written into a counter, and the trains don't check until that counter gets to 0 again. Besides skipping a lot of work, this skips a lot of reading data that's being written to by other threads. There are also the more mundane updates that only involve a single train. This involves the basic acceleration of the train, and also having a max speed that's based on the curvature of the track. Whenever a train gets to the end of a segment in a track, it then goes to the next segment that's described in its path. If that next segment is in a new block, then the train needs to enter a wait queue to enter the next block. And again, blocks are separated by signals. Which wait queue to enter is determined by a pointer that's stored in the block, and I'll go into more details about that in the next section. The point, though, is that there are several wait queues, and each queue is a shared resource, so access to modifying a queue is controlled by a spin lock per queue. If the queues are added to by serial code, then the result is that the waiting entries would be sorted first by the time that they were added, and then by the ID of the train. Since the trains are processed by multiple threads, then the order of the train IDs might not be the same, and so in order to ensure that it has the same order, the queue is sorted by the time and then train ID. This means that the results of the execution by the parallel code is going to be deterministic. It's worth noting that it's also possible to generate errors when proposing a location, for example, if a train doesn't have a next path segment. Finally, it's possible for trains to generate sound effects. Each train has an array of sound effects that it's generating. These basically consist of a chuff while it's moving, chuff, 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 and also a hiss whenever it's stopping, hiss. Since each train has a separate array, no lock is required to modify these arrays. Also, the sound effects are added to in the simulation, but they're not removed by the simulation. Rather, before every frame is rendered, the set of sound effects that were generated is collected and processed. When running either in server verification mode or the ultra-fast simulation mode, then no sound effects are added to the array at all. The next simulation step is to handle trains that are waiting at signals. There are two reasons why a train might be waiting at a signal. One is because the block that the train wants to enter is already occupied. The other is if the train is loading or unloading cargo at an industry or a storage area. If a train doesn't need to wait any longer, then its proposed location is left unmodified. However, if a train needs to continue waiting for whatever reason, then its proposed location is marked as invalid. At first, it seems like resolving waits between trains requires a serial execution. This is because what a train does depends on how other trains behave. For example, if multiple trains are waiting to enter a block and one enters, then that means that none of the other trains can enter. The same is true with industries. Industries might not have enough of a resource for a train to load from, and so if multiple trains are trying to get from the same limited resource, then one of them won't be able to. How do you know which one that is? The solution I came up with is to recognize that some trains are going to depend on each other, but others won't. So what we can do is to determine what are the blocks that depend on one another, and to have all of those interdependent blocks share a same queue, and then the wait entries within any one of those queues are processed serially, but the queues can be processed in parallel. So what we need to do is to figure out what are the different sources of interdependencies. I think the most obvious of these is that all of the signals entering a block depend on each other. And for this reason, instead of storing a pointer to the queue in the signal, I store the pointer in a block, because all of the signals entering a block are going to share the same queue always. We then need to consider how the blocks are connected together. And one of those ways is by chain signals. A chain signal says that in order to proceed, you have to have access not just to the block that is adjacent to that signal, but to a following block afterwards. And so that creates a dependency between blocks. As well, chain signals can be chained, right? So if the entrance to the following block contains a chain signal, then you also are going to depend on the block after that. So you can have an arbitrary number of blocks that are connected by chain signals. Finally, all of the signals that share an industry or that share a storage are going to also be interdependent. And interestingly, in order for this to work, I found a subtle bug, which is that I need to ensure that trains spanning more than one block don't load. Otherwise, you could have an arbitrarily long train, and basically every signal would be able to load or unload from an industry, so long as the train didn't cross itself, I suppose. And so this would cause a nightmare where every block is interconnected with every other block. It can also be somewhat annoying when you're playing if you thought that a train had left a station and it was not going to load or unload, but for some reason the signal is too close and the last train car is still next to a platform and then loads some more stuff. Anyhow, the end result is that we can think of the blocks as vertices in a graph and the interdependencies between the blocks as edges between those vertices. What we need to do then, given this graph data structure, is to find the connected components and create one queue per connected component. I used the union find algorithm to determine the connected components during the simulation initialization. In practice, the results are basically what you would expect, which is that industries generate clusters and they tend to be separated by the stretches of track that are in between. So that's all a bit abstract talking about a graph, so let's look at an example of how this works. Here I have a picture of an industry with various different tracks and platforms and signals. I have a previous video about how signals work, but the basic rundown is that yellow are chain signals, orange are free signals, and blue are block signals. Signals can also be either unidirectional or bidirectional. So in this industry, you can see that they're both terminal stations and roll-on, roll-off stations. So the first thing I do is mark the blocks by these blue vertices to indicate sections of track that are separated by signals. The first thing I do is add edges that are described by the chain signals. I'm coloring these as yellow to match that the chain signals are also colored yellow. Next, all of the blocks that are connected through an industry are connected by edges between them, colored in magenta. All of the blocks are really connected to all of the other blocks, but drawing so many lines would be rather cluttered, so instead I draw them as sort of connected through a virtual block of the industry. This is mostly a shorthand for the illustration, but actually is a little bit how the code works also. Regardless, this shows how we can generate a graph of the connections between blocks, and around this particular industry, you see that there are actually two different large connected components. The stretches of track that are between industries don't really depend on any other pieces of track and act as a buffer. This means that industries tend not to depend on other industries. This means that there tend to be a lot of different wait queues that can be processed in parallel. In my big world map, there were a total of 621 blocks that were then separated into 182 queues. In my smaller example of the level of Birmingham, that consists of 71 blocks that were split into 23 queues. Great, so that describes how blocks are grouped into shared queues, but how do we actually process the trains that are waiting in a queue? If a train isn't loading or unloading, then it will try to reserve a path. The basic idea is that a train can only claim a path through a block if the block has not already been reserved. The simplest case is if the train is waiting at a blocking signal, in which case it only looks at the next block. But if a train is waiting at a chain signal, then it needs to do a depth-first search to find the chains of signals and where is a free path that it can go through. If a train finds a clear path, then it adds itself to the reservation list of the blocks. I'll note that it needs to be a list of trains reserved for a signal because it's possible for more than one train potentially to be in a block if the trains passed through a free signal. But that block may also have a blocking signal entering it, and the blocking signal will require that all of the trains have exited before it allows a train through. Situations in which you would want a free entering and also a blocking entering into the same block are probably somewhat rare, but it is possible to create a priority signal through this means, where if you have a main line, trains can enter it freely, and you could have a side line enter to the main line with a blocking signal, which is basically a yield. I'll also note here that although multiple trains are potentially entering into a block, it's not necessary to have a spin lock around the reservation array for a block because the trains are going to be guaranteed to be processed serially. Because by definition of the connected components, all of the trains that could be potentially contending with each other are in the same shared queue and processed serially. If a train is loading or unloading, then it's going to potentially create a cargo loader, and the cargo loaders are stored in a single shared global array. Because this is a shared resource, then it needs to be controlled by a global lock. In my case, I'm using a spin lock, but you could theoretically use a mutex also. It doesn't really matter. In terms of accessing shared global arrays, it's also possible for the simulation to generate errors at this point. For example, if a train can't reverse at a terminal station, or if there is an invalid path found. As I mentioned before, if the train needs to keep waiting, then the proposed location is marked as invalid. However, if the train can proceed, then the wait entry is removed from the wait queue. Again, this is an array that's shared by multiple trains, but because those trains are all going to be guaranteed to be in the same queue that's processed serially, then again, I don't need to have a lock controlling access to that queue. It can just be freely modified. Whew, okay, well, that was the hardest part, and I promise you that the rest is going to be easier going forward. So let's take a breather. Also, if you want to get more development updates, subscribe to the channel and ring the bell. Once the waits have been resolved, then the next step is to commit the movement of the trains. There are a couple of steps to this, but at its heart, the main idea is to update the location of the engine with the proposed location. In this context, the location is just the distance along the track, And then additionally, once we move the engine, then the cars that are following the engine also have to have their positions updated. The cars' positions weren't proposed during the proposed location step, they simply implicitly follow the engine. This part is only modifying a single train in place, so there's no contention between threads. If the train is moving at this point, then it will also consume some fuel and make puffs of smoke. The smoke puffs don't have any importance to simulation, but they do provide some visual interest. The smoke puffs are stored in a global shared array, and access to the array is protected by a spin lock. Again, this could be a mutex, but it doesn't really matter. If a train runs out of fuel, it can also produce an error, which is again protected by mutex. This brings us then to the most expensive part of committing the train's movement, namely updating the train's attributes. In terms of most of the simulation, the location is just the distance along the track, but the actual 3D position of the cars is also needed sometimes, in particular for collision detection. So the position is considered an attribute that's determined from the distance along the track. And as well, there are some other attributes, such as the slope and curvature, that are required. The slope and curvature affect the acceleration and the max speed of the train. Once the positions have been determined, it's then necessary to update the collision acceleration structure. The collision acceleration structure is just a grid of tiles, and the trains that are in a tile are added to that tile, where the bounding box of the train is also expanded by 2 times the collision radius. This allows for a single point query to determine all of the trains that are potentially collidable. Every train stores the range of tiles that it was in before and calculates a new range that it is in now. If those are different, then it will remove itself, then add itself back to all of the relevant tiles. Because the tiles are shared between different trains, each tile has a spin lock protecting the array of train IDs that are stored within it. Because these arrays are only modified when a train moves between different tiles, they actually aren't updated all that frequently. Trains also tend to be spread out reasonably evenly across the entire map, and so it's not that big of a problem of trains trying to contend on a single resource, because they aren't necessarily going to be accessing the same set of tiles. This brings us to collision detection, which is actually surprisingly fast. Collision detection is funny in that it doesn't actually directly affect the simulation. The only role it serves is to produce an error if trains collide. So as long as I knew that trains couldn't collide, in theory this entire thing could be skipped. But it can't be, so here are the details. Every train is processed in parallel. And there's a simple optimization, which is that if a train isn't moving, then nothing needs to be done for it, and it can be skipped. As well, since the train is moving forward, it can only have the engine run into anything. So I only test one point, which is the engine, for the source train. In the previous step, I had built the list of trains that are in every collision tile. So the first thing I do is get what is the list of trains in the tile containing the engine. Then, for every train in that tile, I detect if the engine collides with it. My collision test first consists of a course rejection, which is determined just from the bounding box of the other train. And if I can't reject the collision, then I do a fine-grained detection where I determine if the engine intersects any of the train cars of the target train. I'll note that this test is not symmetric, because I'm detecting just the engine versus the entire other train, which means that I have to do n times n-1 collision detection tests. If the collision detection were symmetric, then I would only need to do half as many tests. But overall, I think this is a win because it avoids having to detect the collision of every car versus every other car in the other train. This brings us then to the next step in the simulation, which is also the first step that I didn't parallelize, namely adding cars and trains. The thing is that this step is already extremely fast, and it's something that isn't run through the entire simulation because at some point all of the trains have been added. Once the trains have been added, I set a flag that says that this stage is complete, and then these functions aren't called at all in the future. The actual checks to determine if a train can be added or not are also extremely fast, so performance is just not much of an issue. And this brings us now to the last step that I parallelized. This is also the first step that isn't related to trains. Every simulation tick, industries need to consume resources and generate products. This is also the first case where the code actually is completely trivially parallelizable. There's no interaction between industries, and also there are no errors that can even be generated. This brings us to the next step, which is updating the cargo loaders. This is perhaps more interesting because of its simplicity than anything else. For most of the time, a cargo loader doesn't need any update because its movement is completely deterministic, and so there's no update to position or anything like that. It's entirely implicitly defined by its starting time and ending time. The only properties of a cargo loader that are relevant to the simulation are the start time, the delivery destination, and the finish time when the cargo loader needs to be removed. These times are specified as integers, denoting what simulation tick they occur on. This code isn't parallelized because, first of all, it's extremely fast. Most of the time you just loop through and do nothing, and even when you do need to do something, it's very simple. It's basically just incrementing a resource counter. Also, it would be excessively hard to parallelize. Delivering cargo is actually not too bad because that would basically just have an atomic increment. But removing the finished cargo loaders would be pretty slow or potentially difficult. The simplest solution I can think of would be to copy the cargo loaders to an entirely new array and just not copy them over if they're intended to be removed. Whenever adding a cargo loader to the new array, then there would be an atomic increment. But atomic increments are slow, and that would be orders of magnitude slower than just doing the code serially. This brings us to handling smoke, which is similar to the cargo loaders, except that it's even simpler. Again, the movement of the smoke is entirely deterministic just from the initial conditions, and there's a tick at which smoke puffs need to be removed. This is done serially, and in fact as a single line of code. And for completeness, the final step of the simulation is to update the game state. This is generally extremely fast and just checks whether the win conditions of a level have been satisfied or not. If the conditions have been satisfied, then it will update the unlocked regions in the world, it'll save the best time and the solution, and it will submit the score and the solution to the server for verification. But in the vast majority of the cases, namely every tick except for one, none of those steps are done. Now that we've gone through all the details, maybe we can look at that section timing a graph and appreciate it a little bit more. It's somewhat impressive that we got any speedup updating the track occupancy at all, because it wasn't trivial and it's also extremely fast. When proposing a new location for a train, the trains are reasonably independent, but they do have to share access to queues and potentially search for other trains, although infrequently. So we're able to get a decent speed up there. Resolving the weights and cargo loading is probably the thing that we got the least impressive speed up from. This is also the thing that was the hardest to parallelize because there's inherent interdependence between the trains that needs to be resolved. This section took the most explanation and required building a graph of the interdependencies and statically determining connected components. Because those connected components vary drastically in size, sometimes they're a single node and sometimes it might be a dozen, The end result is that the workload balancing is probably not the best. And also there's some other things that the trains are going to communicate with other trains on. For example, they have to access some shared arrays for the cargo loaders. So this just didn't parallelize as well as some other things. That said, it still got a speedup and was worthwhile doing. Committing movement was by far the slowest thing and also got a pretty good speedup, so I'm pretty happy with those results. Collision detection is also pretty fast with very little interaction between the trains. And finally, updating the industries was by far the standout winner of the speedup percentage. This was the most trivially parallelizable step of the entire simulation, but it didn't take a huge amount of time in the first place, so didn't actually reduce the overall time as much as I might hope. All of the other steps were left as serial, but they don't take very much time in total, and so Amdahl's law doesn't really strike me too badly here. So, in conclusion, starting the process of parallelizing my code, it wasn't clear to me that parallelization was even going to be possible. The basic problem is that the amount of time that is spent on a simulation tick is extremely small in the first place, and the simulation ticks are composed of multiple different steps, so the amount of time that a parallel section has is even smaller because of that. What this means is that the overhead of just kicking off some parallel work is extremely important. And my initial tests with some off-the-shelf libraries showed that the overhead was too much to get any benefit whatsoever. And the code went significantly slower just by virtue of launching parallel work. My previous devlog was a video that went into details about how I dealt with that part of the problem. The second issue that I address in this video is that the simulation is not trivially parallelizable, so it's not even clear if I'm going to be able to get a speedup regardless of whether there's any overhead from launching the work or not. This is because the trains inherently interact with each other, and that's what makes the game any fun to play. Trains follow each other, they can collide with each other, they have to negotiate exclusive ownership of blocks, including with chain signals, and trains share limited industry resources. I resolved these issues with a couple of different techniques. The first was to break the dependency cycle of trains updating their position while reading the position of other trains. I did this by splitting a train's position into a current location and a proposed location. This required modifications to simulation throughout, being careful to consider the context of how a position was being used. The next technique was to split a single global weight queue into independent clusters of queues using graph analysis. The idea here is that as long as I can prove that blocks are not going to interact with each other, they can be split into separate queues. The last major technique I used is to use fine-grained locking of one spin lock per some resource. Specifically, I had a spin lock per track segment, per block, per weight queue, and per collision tile. The idea here is that if there are a lot of instances of a resource, even if there are a lot of trains, the chance that two trains are trying to access the same resource at the same time is going to be relatively rare. This means that locking a resource actually has a fairly small overhead in almost all cases. Thank you for watching my video. I hope you got something out of it. If you have any questions or comments, please feel free to write something down below. As I mentioned earlier, this is also the conclusion of a multi-part series of videos. So if you found this interesting, please feel free to go back and watch some of the previous videos for some more information or context. Also, if you haven't done so already, please feel free to like the video or to subscribe to the channel.